UWB is an emerging technology for object-level localization, but current methods rely heavily on distributed sensing, meaning you need many devices, like iPhones, or a direct line of sight to the target, which isn't always practical. Existing UWB methods rely on line of sight to at least 3 calibrated anchors with known positions in a small area, but this isn't feasible in large environments like seaports. And it is not likely one may spend thousands of UWB anchors in the region. Even with LiDAR, it can get lost in this large repetitive jungle easily with one-shot localization. Traditionally, all UWB sensors are placed in the line of sight and least squares calibration is performed. Even with proper calibration, the solution will still drift if there is only 1 or 2 UWB in view, as demonstrated by the latest state-of-the-art methods. We solve this by combining UWB data with LiDAR odometry and applying Gaussian processes to estimate anchor positions, even in non-line of sight conditions. This ensures accurate calibration in large-scale environments. And we verified the solution using a map constructed from hundreds of scans for seam and level accuracy. As we collect LiDAR and UWB data while moving through the environment, our system calibrates the anchors using Gaussian processes. With sufficient samples along the trajectory, the anchor's position can be represented as a radio heat map for inference. In tests over a 600 by 400 meter area, our method achieved a 2.03 meter average error. Our error is less than 1% of the total space. GPS, in comparison, struggled with significant drift in the same conditions because of the heavy occlusions and tall buildings. Most of the other calibration methods, commercially available or state-of-the-art, simply fail to work. It shows that we are able to get SOTA performance on calibration. One might ask the benefit of calibration without line of sight to multiple UWB anchors. The answer is that UWB helps filter out outliers, enhancing one-shot global localization in repetitive environments. Our focus is on effective range-based filtering on top of the existing methods, such as Stable Triangle Descriptor (STD), which is only able to get 30% cross-sequence success rate. We show that using UWB anchor positions as a filter significantly improves results and reduces processing time by offering a 30% higher localization success rate. The experiment, conducted on a NUCPC, demonstrates its suitability for field robotics. Our approach is the first work that shows that UWB, combined with LiDAR and Gaussian processes, can overcome calibration issues in large environments. This makes localization systems more accurate and faster without requiring expensive infrastructure. For details, please refer to our papers.